Welcome back to my YouTube channel or the VIG Structural Hub. This is the #1 channel for structural insight and a place where you learn, build, and innovate. Today, I want to tackle example number 1, and this is the design of one-way spanning solid slab, and we'll specifically designing a simply supported slab. So today, as I have said, we will tackle what we call simply supported slab. This is a slab resting on 2 supports. And then after this, we will tackle what we call simply supported slab with an overhang. Then from there, we'll tackle what we call continuous one-way spanning slab. So the question is on the board and it reads, figure below shows a floor plan of residential building using the data below. Determine the effective depth of slab and hence determine areas of main steel, distribution bars or secondary bars, and check for deflection. So this is the plan. As you can see, you have been given a variable action, which is QK as 2.0 kilonewton per meter square. Then you have the floor finishes is equal to 1.5 kilonewton per meter square. Ceiling and the services is equal to 0.5 kilonewton per meter square. Then the unit weight of concrete is equal to 24 kilonewton per meter cubic. Then the dimension R from here to here is 6400 millimeter. And then from here to here is 2500 millimeter. Additional information, FCK is equal to 30 Newton per millimeter square, FYK 500 Newton per millimeter square, and exposure condition is equal to XCL. So let's see how we can tackle such a question. Solution. The first thing to do is to check whether this slab is a one-way spanning or a two-way spanning. So to check, you need this ratio Ly over Lx, whereby Ly is the longer span and Lx is the shorter span. So this one is equal to 6.4. You can change this to meters, or you just work with millimeter. The answer will be the same, over 2.5. So this one will give us 2.56. 2.56. So 2.56 is greater than 2, and therefore one-way spanning slab, like that. From there, we will proceed to estimation of D, or depth of slab. Estimation of D. So to estimate D, as you saw in the introduction to design of one-way spanning slab, you assume a reinforcement ratio. So you'll say assume a reinforcement ratio is equal to 0.35%. So for a lightly reinforced concrete, the ratio must be less than 0.5%. 0.5%. So it must be below this one. After assuming a reinforcement ratio, which is equal to 0.35, the next step is to write the basic length over depth ratio formula or expression 8.32. And after doing so, define the terms in this expression. So to define the terms, this is what I mean. This one we have seen, this one is the assumed reinforcement ratio, which is equal to 0.35. Convert it into fraction. So you divide it by 100. This one will give us 0.35 divided by 100, 3.5 times 10 is power negative 3. And then we come to this one. So this one is given by square root of FCK, square root of FCK times 10 is power negative 3. So this one is equal to FCK is 30. So this one is equal to 30 raised to power 0.5 or a half or a square root of 30 times 10 raised to power negative 3. So this one is equal to 30 raised to power 0.5 times 10 raised to power negative 3. So this is 5.48 times 10 raised to power negative 3. And then 1.5 square root of FCK is equal to 1.5 square root of 30 will give us 1.5 times square root of 30, 8.22, 8.22, like that. And then 3.2 square root of FCK. This one is equal to 3.2 square root of 30. So this one will give us 17.53. 17.53. After doing so, insert the known values into the formula. So let's do it. L over D is equal to K. K is 1.0 and it is obtained in table 8.22 or 8.11. I will show you. And then open the bracket, 11 plus, this one is here, 8.22 times 5.48 times 10 raised to power negative 3 all over 3.5 times 10 raised power negative 3, like that, and then plus you come to this one, 17.53 into bracket 5.48 times 10 raised power negative 3 all over 3.5 times 10 raised power negative 3 minus 1, and then raised power 3 over 2. And then everything will multiply by 1. So this one is equal to 1 into bracket 11. Then you come to this one. This is 8.22 times 5.48 times 10 raised power negative 3 all over 3.5 times 10 raised power negative 3. So this is 12 plus 12.87, then plus this one. Let's begin with this one. 5.48 times 10 raised power negative 3 all over 3.5 times 10 raised power negative 3, then minus 1 raised power 3 over 2, then times 17.53. So this is 7.46. 7.46. So let's open the bracket. 11 plus 12.87 plus 7.46. So the answer is 31.33. So we take 31, we take it as 31. And then from there, we know that L over D is equal to 31. But L alone is equal to this shorter span is 2.5. Therefore, D, make D the subject of the formula. This one will be L all over 31, which is equal to 2500 all over 31. So this one will give us 2500 divided by 31. So this is 81 millimeter. Since 81 millimeter is very small, 81 millimeter is very small, I want to take D. Therefore, you can say take D as 120 millimeters, which is greater than 81 millimeters. The reason as to why I'm taking 120 millimeter, I want to design a slab. I want to have a slab which will have H as 150 millimeter. But if you take 81 to arrive on 150 millimeter, it will not be possible. So take a value which, when you add, because h is equal to d plus a half of the main diameter, and then plus cover. So this one, I'm aiming to 150 millimeter. But if you work with 81, then it will not give you 150 millimeter. So take D as 120 millimeter. Then after doing so, you will say, assume main diameter is equal to 10 millimeter. And we have been given an exposure condition as XC1. Therefore, we need to calculate the nominal cover. And to calculate the nominal cover, you will say minimum cover is equal to the maximum of minimum cover for durability maximum of minimum cover for durability, and then another one is the C minimum, which is given by the diameter of the bar, and then we have 10 millimeters. Like that. So for class XC1, C minimum durability is equal to 15 millimeters. So this one is obtained in table 8.10. 8.10. So I show you the table. The first table is table 8.11 and 8.10. And then the C minimum is equal to 10 millimeters. So the C minimum will be the minimum of these three, no, the maximum of these three, which is 15 millimeters, which is 15 millimeters. So nominal cover to reinforcement, is given by C minimum plus the deviation cover, which is 10 millimeters. So this one is equal to 15 plus 10 millimeters, which is equal to 25 millimeters. So nominal cover is equal to 25 millimeters. So let me show you table 8.10 and table 8.11. So this is table 8.11, and it is a table for basic span over depth ratio for reinforced concrete members. You can see where the cursor is. So we begin by the first column, which is for the structural system. We have the simply supported beam and slabs. Number 2, end span of continuous beam and slabs, and so on. So K is 1.0 for simply supported beams and slabs. So that is what I used. And then we have the highly stressed concrete and then the lightly stressed concrete. So for lightly stressed concrete, the ratio is equal to 0.5%. So it must be below that one. So that is all about table 8.11. I proceed to table 8.10. So this is table 8.10, minimum cover reinforcement for durability. So for this, we proceed to a class XC1. So as you can see, XC1 is 15. It is 15 for class for strength 30. You can see it's 15. So that is again how you read that table 8.10. Now let's calculate the H. So H is given by, this is the overall height or depth. So H is equal to D plus main bar diameter all over 2 plus cover or nominal cover. So this one is equal to D is 120 plus the main bar is 10 all over 2. Here it is, and then plus 25. So this one is equal to 120 plus 10 over 2 plus 25. So this is 150 millimeters. So this is H. So the depth of slab or slab thickness is equal to 150 millimeters. So that is how you calculate or how you estimate the depth of slab. Therefore, slab thickness stroke depth is equal to 150 millimeters. After there, we proceed to what we call load calculation or load analysis. Load analysis stroke calculation. So we will start by the self weight of slab. So the slab has a thickness of 150. So convert 150 into meters, divide it by 1,000, then multiply by the density or the unit weight of concrete, which is 24 kilonewton per meter cubic. So times 24, you will get 150 all over 1,000 times 24. So this is 3.6 kilonewton per meter square. So remember this. Know how to work with units, because this one is in meter and this one is in kilonewton per meter cubic. So meter here 1, meter here, meter square. So the answer will be 3.6 kilonewton per meter square. And then from there, we have been told that the floor finishes is equal to 1.5 kilonewton per meter square. So total permanent action, which is GK, is equal to 3.6 plus floor finishes, which is 1.5, plus ceiling and surfaces 0.5. And remember, it is in kilonewton per meter square. So kilonewton per meter square. 3.6 plus 1.5 plus 0.5. So this is 5.6. So this is 5.6 kilonewton per meter square. And then we come to the QK. So QK is equal to 2.0 kilonewton per meter square. So the design ultimate load, is equal to 1.35 GK plus 1.5 QK, then multiply by you multiply by 1 meter width of the slab. So times 1 meter width of slab, because we are designing this slab in a 1 meter width strip. So this one is equal to 1.35 times GK, which is 5.6, plus 1.5 times 2. Then you multiply by 1 meter. So this one is equal to 10.56 kilonewton per meter. So this is the design ultimate load. So to deal with these units here, if you multiply this one, you will get 10.56, and the unit for this is kilonewton per meter square, then times 1 meter. So this meter will cancel here meter. So the final units will be 10.56 kilonewton per meter. So that is how you work with units. And from there, we can now draw our slab here. So this is the loading. It is a UDL 10.56 kilonewton per meter, and it is spanning 2.5. Remember, for a one-way spanning slab, the main reinforcement is provided at the shorter distance, which is 2.5 meters or 2500 millimeters. Then from here, you can now calculate the design ultimate moment, which is given by M ED is equal to W L square all over 8. So this one is equal to 10.56 times 2.5 square all over 8. So this one is equal to 10.56 times 2.5 square all over 8. So this is 8.25 kilonewton meter. So after calculating the ultimate design moments, the next step is to calculate K naught, which is given by MAD all over FCK BD square. So this one is equal to MAD is 8.25 times 10 to the power of 6. Change it from kilonewton meter to Newton millimeter. FCK is 30 times B. B is 1,000. Remember, we are designing this slab as a 1 meter strip, which is the B. So 1 meter, convert it to millimeter, you will get 1,000. Then times D, which is 120 square. So this one is equal to 0.019, and therefore 0.019 is less than 0.167. Therefore, no compression. Reinforcement is needed. We proceed to area of tension steel. AS1 is equal to MAD all over 0.87 FYKZ. What follows next is to calculate the area of steel in tension, which is the main bar, is equal to M ED over 0.87 FYKZ, but Z is equal to D so this is Z, and it must be less or equal to 0.95 D. So Z is equal to D, which is 120, K naught is 0.019. Raised power 0.5 or a half, and it must be less or equal to 0.95 B. So let's check. 0.25 minus, this is 3 times 0.019 all over 3.4 raised power 0.5. Plus 0.5. So this is Z is equal to 0.98 times 120. So this one is greater than 0.95 D. Therefore, Z, we will adapt 0.95 D as our Z. So this one is equal to 0.95 times 120, which is equal to 0.95 times 120, 114 millimeters. So this is Z. So area of steel is equal to MAD, which is 8.25 times 10 to the power of 6. Change it from kilonewton meter to Newton millimeter, all over 0.87 times 500 times 114. So this one will give us 8.25 times 10 to the power of 6 divided by 0.87 times 500 times 114. So this is 166 millimeter square. And then you'll say from table 3.22 provide H10 at 300 millimeters center to center, and area of steel is equal to 262 millimeter square. I do hope you know how to read this table. If you don't know how to read it, let me know in the comment section. After obtaining this, we can now easily calculate our new reinforcement ratio. So this is how you calculate the reinforcement ratio after getting this reinforcement bar size and spacing. So the required reinforcement ratio in this case is equal to all over BD. So this one is equal to 166 all over B. B is 1,000 and D is 120. So this one is equal to 166 all over 1,000 times 120. Then multiply by 100 so that you can have it in percentages. 0.138%. 0.138%. From there, you can check estimated effective depth of slab. So check again. Estimated effective depth of slab and deflection So for this case, you will say the design service stress is given by is equal to 5/8 FYK times area of steel required over area of steel provided. So 5/8 FYK times area of steel required over area of steel provided is equal to 5/8 times 500. Area of steel required is 166 over area of steel provided is 262. So this one is equal to 198. The modification factor is equal to 310 all over design service stress. So this one is equal to 310 over 198, which is equal to 1.6. And this 1.6 is equal to K, like that. From there, we again calculate the basic length over depth ratio, which is given by K like that. And then you define the terms and insert the known values into the formula. So in this formula, let's insert what is known in this formula. So L over D is equal to K is 1.6, open the bracket. So this is 11 plus 1.5. We already have this one, 1.5 times 30 raised per half times 5.48 times 10 to the power of -3 all over 1.38 times 10 to the power of -3. For this one, we use a 1.38, which is equal to 0.138 percent. So you convert it to fraction. So divided by 1,000, you will get, no, divided by 100, you will get 1.38 times 10 raised to power of negative 3. And then plus 3.2 times 30 raised to power half, 5.48 times 10 to power of negative 3 all over 1.38 times 10 to power of negative 3 minus 1 raised to power 3 over 2. So this one is equal to, if you carry out the operation, you will get L over D, which is equal to modification allowable stress, is equal to 1.6 into bracket 11 plus 11 plus 32.63 plus 87.76. So this one is equal to 213.424. And this is the allowable limit, or the modification allowable ratio. So this is the modification allowable ratio, like that. So we proceed. The actual span over depth ratio, the actual span all over effective depth ratio is equal to L over D, which is equal to 2500 from here to here, all over 120. So this one is equal to 20.83. By comparing 20.83 with this one, you can clearly see that 20.883 is less than 213.424, and therefore the slab is okay. Therefore the slab is okay. Is okay and meets deflection equation. Like that. Deflection requirements, not equation. Deflection requirements. And then from there, you can say that therefore use a slab of effective depth of effective depth 120 millimeters H, 150 millimeters, and main steel and main steel H8, H10 not 8, at 300 millimeter center to center. We proceed. Check bar spacing. Bar spacing and steel areas. And steel areas. So for the maximum spacing, maximum spacing for main steel, we know that it must be 3H must be less or equal to 400 millimeter. So this is generally. So let's check 3 times 150, which is equal to 450. So this one is greater than 400 millimeters. So we'll use 400 millimeters as our maximum. So maximum spacing will be 400 millimeter. And the one we have been provided due to the steel designed is 300 millimeter center to center, which is less than 400 millimeter. Therefore, okay in general. And then we proceed to maximum spacing in areas of maximum moment. So in areas of maximum moments, this parameter will apply. So 2H must be less or equal to 250 millimeter. So this is 2 times 150, which is equal to 300 millimeter, and it is greater than 250. Therefore, we use 250 as our maximum, but 300 millimeter center to center is greater than 250 millimeter. Therefore, we will adapt 250 millimeter center to center. So we'll use 250 millimeter center to center instead of 300 millimeter center to center. So use H8 or provide H10 at 250 millimeter center to center. So we proceed to steel areas. We know that 0.04 AC, it must be greater or equal to area of steel 1, and this one must be greater or equal to 0.26 FCTM FYK BTD, and this one must be greater than or equal to 0.0013 BTD. So 0.04 AC is equal to 0.04 AC is the area of the concrete, which will be 1,000. This is 1 meter times H 150. So this one is equal to 0.04 times 1000 times 150. So this is 6,000 millimeter square. And then AS1, this is the area provided, which was, or which is, let me check, that 266, which is I think it is 262 millimeter square, and then 0.26 FCTM over FYK is given by this formula. This one is given by this formula, 0.26 times 0.3 FCK raised to power 2 over 3. So 0.26 FCTM. Now let's now put the values in the formula. So this one is equal to 0.26 times 0.3. FCK is 30 raised to power 2 over 3, all over 500, then times BT, this is 1000, times D, which is 120. So this one is equal to 0.26 times 0.3 times 30 raised to power 2 over 3, all over 500 times 1000 times 120. So this is 181 millimeter square, and then you proceed to 0.0013 BTD. So this one is equal to 0.0013 times 1000 times 120. So this one is equal to 0.0013 times 1000 times 120. So this is 156 millimeter square. Therefore, we can just write the values. So 600, which is this one, 6,000 is greater than this one, 262, which is greater than 181, which is greater than 156. Therefore, okay. We proceed to secondary reinforcements. So for secondary reinforcement, you know that area of steel for secondary or transverse, it must be greater or equal to 20% times area of steel. This is for main, like that. So we can replace this sign with equal sign. So secondary or area of steel for secondary is equal to 20 over 100 times area of steel for main. This is 262. 262. So this one is equal to 52.4 millimeter square. And this one must be greater than this. So the area of steel for secondary bars must be greater than this. Therefore, hence provide from table 3.22. Hence provide from table 3.22 H8 at 300 millimeter center to center, and area of steel provided is equal to 168 millimeter square. So that is it. And then we check for maximum bar spacing. Maximum bar spacing. So for maximum bar spacing, so S max is equal to 3.5, H must be less or equal to 450 millimeters. Therefore, this one is equal to 3.5 times 150, which is equal to 525 millimeter. It means this one will be used as the maximum spacing, because this 552, it is exceeding 450 millimeter. It exceeds 450 millimeter, and henceforth and therefore the minimum, which is 300 millimeter, is less than 450 millimeter. Therefore, okay. So this is general. And then for the areas of maximum moment, where bending moment is high, areas of maximum moment, 3H must be less or equal to 400 millimeter. So 3H is equal to 3 times 150, which is equal to 300 millimeters. So this is the maximum. Therefore, the minimum, which is 300 millimeter center to center, is less than 400 millimeter. Therefore, okay. So for the secondary bars, provide H8 at 300 millimeter center to center. So we proceed to crack width. So here we'll just write a statement, and we'll say that since the overall depth of slab does not exceed 200 millimeters and the rest of the code provision have met no further measures specifically to control cracking is necessary. Like that. And then for the shear, no need to design for shear, because you remember in the code, in the introduction, we saw that for beams which has less than 200, no, for slabs which has less than 200 millimeter thick slab, no need for designing or no need to check for shear or design for shear. So if you want to do it, you can do it for your own benefit, but there is no need for shear reinforcement or shear calculation. So we end there. What is remaining is to draw the section and elevation. So remember, the main steel is provided at, which is H8, no, H10 is provided at 250 millimeter center to center. So if you want to draw an elevation, this is how it will look like. So this is the main steel. So, and we have the distribution bars. So this one will be distributed at a span of 1.2, no, 2.5 meters. So this is 2500. So to get the number of steel, you'll take 2500 all over 250, then plus 1. You will get 11 in number. So this one are 11, 01, H8, 300, no, 250, center to center. And this one are the distribution bars, all of them. So this one is distributed at this distance from here up to that point, which is 6400. So to get the number, take 6400 100 all over 300 plus 1. So you will get 6400 all over 300 plus 1. So this is 23. So this one are 2302. This one should be H10, not H8. H8 300 center to center. And this distance is equal to 150 millimeters. And this one 120 millimeters. So this is an elevation. If you want to draw in the plan, this is how you will do. So this one is the 02. This one is the 02. So this one is 2302 H8 300 center to center, and this one is 11 01 H10. Let me write it here. 11 01 H10. To 50 center to center. So that is how you draw. So that is it, and the question ends there. So we meet again in my next session. Don't afford to miss. Subscribe, like, comment, and share. So thank you for your time.